the algebraic derivation of the position equation. In physics, if we talk about the position equation, we're talking about this bottom highlighted equation right here. And it says that your position as a function of time is related to x naught, which is your original position, v naught, which is your original velocity, and the acceleration. Okay? And to get to that point, we have to start with the other three highlighted things. Okay? And all of those are just fundamentals of how we actually define what velocity is and what position is. So let's look at this middle one first. This would be the absolute most basic position equation that you've used since you were like in third grade. Where you are located is where you started plus what you did and for how long. So for instance, if I started 10 meters to the right and I was traveling 5 meters per second for 5 seconds. Well, if I traveled 5 meters per second for 5 seconds, that means I must have traveled a distance of 25, plus if I started at 10 meters, I now am at an x value of 35. This equation is always true and will always be true. It is the definition of average velocity. I don't care what you're doing in an interval. If you tell me you know your average velocity during an interval, and you multiply by the time you went, that average, I will then tell you how far you went. And if I add it to where you started, I will then predict where you ended up. So this is literally the definition of position and velocity in time. Now, I say it's the definition, but it also is very unuseful. The reason is we almost never know the average velocity during a trip. We know instantaneous velocity, we know initial velocity, we know acceleration, but we rarely actually know the average velocity, right? You were walking and then you were jogging and then you were sprinting and you changed direction. We know all of those details. We rarely actually know what on average you did. However, that equation is still true. Where you're located, x, is where you started plus on average what you did for whatever amount of time, right? Velocity is the rate of change. It is the slope of that position graph, okay? So that is a true statement. Now let's look up here. This is the velocity equation. This is also one of the big three, and there's no derivation to it because it is the definition of velocity, right? When we say VF, V final, that's the same thing as just V equals, right? V is the final velocity. So if you wanted to know your final velocity, what would you have to know? Well, you'd have to know what you were traveling at the beginning, right? Your initial velocity plus some AT. Acceleration, by definition, is the rate at which you change your velocity, right? For an example, an acceleration might be 5 meters per second squared. That means you're increasing your velocity by 5 meters per second every second. So if you take an acceleration times a time, that will then give you how much you changed your velocity by. Example, if you have an acceleration of 5 meters per second squared for 2 seconds, that means you increased your velocity by 5 meters per second for 2 seconds. That means you increased your velocity by 10 meters per second. And if you add that to your original velocity, you then have your final velocity, right? Velocity is linearly related to acceleration. It is, by definition, acceleration is the rate of change of velocity, thus the slope, and it makes sense that it is then AT. Okay, so velocity is linear to acceleration, V equals V naught plus AT. And then we also have another definition of average velocity. And again, all of these things are assuming constant acceleration. Okay, and we'll go over what happens if it's non-constant, but almost all of physics ends up being constant acceleration. And this is also a true statement. The average velocity, if you take your initial velocity plus your final velocity and you divide by 2, it will be the average. And again, that is only true because the velocity is linearly increasing, meaning a constant acceleration. Thus, halfway is the average. If you went from 5 and you went to 15 and you had a constant increase of that, I guarantee on average you were going 5. or excuse me, 10, because you were going 5 for the same amount of time you were going 15, you were going 11 for the same amount of time you were going 9, and so on, right? The middle velocity is in fact the average when you have a constant acceleration. Okay, and again, that's not always true, but this is true under constant acceleration. And then the rest of this derivation is just showing you where this bottom equation came from, right? So we look at this bottom equation, it's got this 1/2 AT squared, and we're wondering where that term came from. Well, it just came from algebra. There's nothing tricky about it. So if we take the first 3 highlighted things that are by definition what we mean by position and velocity and acceleration, if we use those things, we can derive this equation. So again, average velocity, v naught plus vf divided by 2. It's just saying that the average velocity must be the middle. The velocity equation as a function of time is how fast you were going at the beginning plus what you did to change that velocity and how long. Okay, so if you take this equation, v naught plus at, and you substitute it in to the top, vf, you get this equation right here. If we simplify that, we get 2v naught plus at over 2. If we distribute the half to both of these terms, we now can say that the average velocity is v naught plus 1/2 at, right? At over 2 is this 1/2 at. If I then take that and I plug it in for the average velocity into that equation, I get this. If I distribute the t to both of these terms, I then get what we call the position equation. That your final position is equal to x naught plus v naught t plus 1/2 at squared. I algebraically showed you where this equation came from the basic definitions of what velocity and position equations are. And just as a reminder, I write it here, this is the standard position equation. We will use this equation 1,000 times. We can only use it during a constant acceleration. If the acceleration is not constant, we will need to use calculus. Again, algebra works in almost every scenario in science and math if it's constants. A constant increase, nice and easy, back to 3rd grade, right? Distance equals rate times time. That only becomes void if the rate is a non-constant. If you're not increasing something by a constant, then everything requires calculus. Okay? So all 4, well, actually this one is true for always, but these guys right here, boom, boom, and boom, require constant acceleration, which, probably 99, 98% of the time and all the entire year in mechanics, we will look at constant acceleration issues. If we have non-constant acceleration, we'll have to use calculus, and that will be a further discussion. Okay, so if anyone asks you, where this came from or what's this 1/2 at squared, why is it a square here? Again, this is the algebraic derivation of it. We also can look at the units and the dimensional analysis of this equation later, and we will derive this exact same equation using calculus later on in the course. When I say later on, I mean just give me 3 days and we'll show another approach to this.